So this is the image sequence that we're going to run. So now here we have run it through. Now we're going to do all the operations here on the images. We're printing out down here, we're printing out the transformation that we're actually estimating, or the pose that we're estimating, and also the position in the XY world coordinates here. So down here we can see where are we in the world from one frame to the other frame. Up here at the top we can see all these features here that we're detecting in one image. So we have one image here to the left, and there's the second image here to the right. Hey guys, welcome to a new video in this computer vision tutorial. In this video here we're going to talk about visual odometry with a monocular camera. So first of all, we're going to talk about like what is visual odometry, what can it be used for, how can we set it up. And at the end of the video, we're going to go into the code. We're going to go line by line over the Python script that I have, where we can actually like implement visual odometry. We can see how it works and how good results do we actually like get. So we're going to use visual odometry for a lot of different kind of things, and we're going to cover all of it in throughout this video. But first, remember to join Discord server. I'll link to it down in the description here. You can come to the channel, chat about computer vision, deep learning, AI, and so on. You can also become a member of the channel if you want to support the channel with a small monthly fee. Everything will go to create more and better quality content here on the channel. Also, if you're a member of the channel here, I can also give you some guidance and help with your own projects if you have some problems. So if you're a member of the channel, you can just contact me and I can help you out with your projects. So thank you guys. So first of all here, just to get your introduction here to visual odometry, we're going to talk about like what is actually like visual odometry, what can be used for. We're going to go over some different kind of applications where we can use visual odometry in different kind of like areas. We're going to talk about like, how can we construct it. We're going to look at the pipeline, and then we're going to implement all of it. But first of all, here in the start of the video, we're going to cover like the theory behind visual odometry, how can we set it up, and then we're going to implement that and go into practice and use it in code. So first of all, what is visual odometry here? So the idea and the objective here of visual odometry is to estimate the pose of a camera by examining the changes that motion induces the images. So basically here we just have like a camera. If we, for example, have self-driving cars, we have a dataset here called KITTI. We're going to use this dataset here throughout the video and also in the code later on. But basically here we're just going to look at, we just want to detect features in our images. So we just take frame by frame, and then we can actually like look at those features in our images. We get some specific and unique features in our images with the like the feature detectors that we have. So if you want to know more about feature detectors and so on, different kind of feature detectors, we've covered all of it here in the video, also camera calibration and so on. So make sure to check those videos out beforehand if you want to know more details. In this video here, we're just going to combine like all the things that we've learned throughout this channel, and then we're going to create this really nice visual odometry project here at the end. So here, the objective here is that we want to look at features in different images, and then we want to track them frame by frame. And then when we're tracking it frame by frame, we can actually like estimate the pose of our camera and thereby the trajectory of our camera in our environment. So we want to find the poses of a camera by examining the changes that motion induces on our images. So down here at the bottom, we can see an example of an image from the KITTI dataset. We have this car driving around capturing images with a camera and around with a car, and then we have this KITTI dataset, which is basically just like images from a car. Then we want to reconstruct the environment and track around, like trying to estimate where are we in the environment by using visual odometry here in this car example. It can be used for a lot of different kind of things as well. But here we're tracking these different kind of features where we have like the green dots. So we can, for example, use the SIFT or the ORB like feature detector. Then we can match these features here from frame by frame, and then we can actually like track those features, exact unique features, frame by frame, and then we can use that to calculate the pose of our camera, so we can actually like get how are we actually like changing the pose from frame to frame. So down here we get features that we're going to use. We're going to use that later on, but this is just to show you like what is visual odometry. So here we can see some of the results from visual odometry, like the results that we can actually like get. So we can just by taking the frames in, detecting features in our frames and tracking all the features frame by frame, we can actually like get this really nice map of our environment by estimating the pose of our camera. Over here to the left, we can see like a sequence from the KITTI dataset where we actually like just have this car drive around with the camera, capturing images that we're then doing our feature detection on, and also tracking those features around in the image from frame by frame. We can see the green lines here is actually like the pose of our camera. These are refined poses by using, for example, bundle adjustment and so on, both locally and also for global optimization of the whole path here with the environment. Up here to the right, we can see some other different kind of examples where we just have like the ground truth and also estimated pose. So this is a really nice result that we can get when we're actually like doing global optimization later on. But this video here, we're just going to keep it simple. We're just going to take in like a sequence from the KITTI dataset, and then we're going to use that, implement the visual odometry here, and then estimate the poses for a number of frames in our sequence. So now we're going to talk about some of the applications that we can use visual odometry for. So for example, as we've always seen, we can use it for, like, for example, self-driving cars and robots. So let's say we have an environment with our robot and we have attached a camera on top of our robot. Then we can actually like have it to navigate around in the environment, see what is going on, where are the walls in the environment, and so on. And then we can actually like use that to map the environment, and we can also localize where are we in the environment by using visual odometry. We can combine that with loop closure, so we can actually like close if we've seen some place before, and then we can actually like extend it to visual SLAM. We can also use it for like space exploration. Let's say we send a robot to Mars, we want to navigate around on Mars, and we don't really have other sensors where we can like see how is the environment and so on. Then we can use visual odometry. We get all information about our surroundings. We can combine it. We can estimate the pose of our camera, how are we moving in the environment, and so on. We can also use it just for like mapping of environments and localization in environments. So basically, if we just have a camera attached to something that can move around, we can then capture the frames, look at the frames, how are they matched to each other when we're comparing the features, matching the features in the images frame by frame. Then we can do all these different kind of things here with only a monocular camera. So we're short to talk about like visual SLAM and visual odometry. Here we're going to compare it, like what is the difference between visual odometry and visual SLAM. So the goal of SLAM is actually to obtain a global consistent estimate of a robot path. When we're talking about like only using visual odometry, we're actually like only talking about like some local estimate of our robot path. Then we can actually like close our loop, and then we can get visual SLAM. So the only difference between visual odometry and visual SLAM is basically just like it is SLAM, like visual SLAM is basically just visual odometry with loop closing, and then we can do global optimization when we're actually like closing our loop to get this nice and smooth path, as we can see down here at the bottom. So over here to the left, we can see our path here, or our estimated robot path before we're closing the loop. So we can get a lot of errors, like our errors are accumulating when we're using visual odometry. So that is one strain here to the system. But when we're using it for visual SLAM, for example, we can do loop closing. We can detect the loops that we have. So if we're seeing some frames or like some features before, then we can actually like close the loop and do global optimization. So we get this nice path over here to the right. And this is actually like really close to the ground truth path that we have from our dataset, as we're going to see later on here in the video as well. So the choice between visual odometry and visual SLAM is basically just a trade-off between performance and consistency, and also simplicity in implementation, because like visual odometry is really simple to implement, as we're going to see later on in this video here, where we're going to implement everything in code. I'm going to provide the Python script that we have. So you basically just go into my GitHub, copy paste the repository, and then play around with it yourself. You can just run the Python script, and you can actually like do visual odometry on a sequence from the KITTI dataset. Then we can see the ground truth and also the estimated path, and then we can compare that and look at the error. But over here, if we want better performance, we want consistency, we want a more accurate like view or like mapping of our environment, then we need to do visual SLAM, which is basically just like closing the loop and doing some optimization here globally on our map. So here we can see the visual odometry pipeline. So over here to we can see that first of all we have an image sequence. So in this video here we're using a monocular camera. So we basically just have one single frame, and then we're just taking the next frame, and then we actually like have this image sequence. Then we're going to do feature detection on both of our images. So we have one image, and then we have the next image as well. Then we're going to do feature detection on both the images. Then we can do feature matching, where we're actually like matching the features from the first frame to the second frame, which is basically what tracking is. So we're tracking the features from the first frame to the second frame. Then when we have those, and we actually like have the exact same features in those, we can actually like see that we have some translation from the first frame to the second frame. And then we can do motion estimation, which is basically just doing post estimation of our camera, so we can see how are we moving frame by frame, which is actually like just corresponding to finding or like estimating the path of our robot in the environment with our attached camera. Then we can do some local optimization. We can do bundle adjustment on our frames that we're actually like calculating, but also on our camera poses we can do bundle adjustment on, which we're going to talk about later on in another video. So how we can actually like optimize and do like optimization to those point camera poses that we find with Visual Odometry. So basically Visual Odometry, it computes the camera path incrementally. So we just go pose after pose. So we just take one frame, the next frame, the next frame, the next frame, and then we're actually just calculating the translation or like the transformation from those frames, and then we can just add those together, or like we can actually just multiply those together and get the final pose. So where are we in the environment after all our images, or like been through a whole image sequence. So basically here we have Visual Odometry triangulation. So when we have these features here, we need to match them together frame by frame, and then we want to do triangulation. So let's see here down at the bottom, like we have a first camera, then we see points in the world that is projected down on our image plane in our camera, or like in our first camera, and then we go to the next frame, we have moved our camera, then we see the exact same points in another camera, then we can actually do triangulation between those camera frames. But when we're using a monocular camera, in this case here, we don't have any information about the depth, but we still see the same point from two different viewpoints, so we still have some information about the depth, but we will have something called scale ambiguity with that we need to take into account when we're using monocular visual odometry. In the next video, or like in the future videos, we're going to talk about like stereo vision visual odometry as well, where we have more information about the depth of our points, or like a 3D world points in the real world that we want to do, or like we want to use to do post estimation from one frame to the other frame. So we're going to calculate the relative scale as we're going to show you in the code, so we can actually get some idea about the depth in our image, because we need those 3D points to estimate the pose of our actual camera. So the solution is found by determining the transformation that minimizes the reprojection error of the triangulated points in each image. So we just talked about we want to triangulate the points that we found in both the images, and then we want to minimize the reprojection error, because we actually reproject our points down on the image plane from our 3D world point. So we want to minimize that, because then we get a better solution, we get a better transformation from the one frame to the other frame, which is actually just the pose of our camera or our path or trajectory. So here, basically, to find that, we need to find the essential matrix, because when we have one image and we have some point in one of the images and we want to project that over to another image, we can use the essential matrix. So basically, the essential matrix can be computed directly from the image coordinates, and we need at least 5-point correspondence. So we need all those different kind of features. The more features we have, like the better result that we get. And then we can actually, when we have our 5 correspondences here, we can estimate our essential matrix. And then when we have our essential matrix, we can actually just map points between one frame and the other, and then we can decompose that essential matrix into a rotation and a translation vector. So basically have our rotation matrix and our translation vector. When we combine that, we actually have our transformation. So then we actually have a transformation from one image frame to the other image frame, which is actually just the resulting path of our camera. But when we decompose our essential matrix, we will end up with 4 different kind of solutions. So all these 4 different kind of solutions we can see at the top right corner here. So we get all these different kind of solutions, but then we actually need to go in and check like all the different kind of values, and we want to take all the points that have the most positive C values in our image, because then we will end up with the case in the top left corner here over in the 4 different kind of solutions that we get. So we don't want the point to be behind the cameras, or like one of the cameras or the other camera. We want to have all the points in front of the camera. We need to find that solution when we actually decompose our essential matrix to a rotation and the translation vector. So we want to find that. We just look at we just look at the solution with the most positive values that we have, and that will be our resulting, or like our result, which will be our transformation, and then we use that transformation to actually generate our path with Visual Odometry. So the last thing here that we're going to talk about is basically just when we want to go from Visual Odometry to Visual SLAM, we can do loop detection. Over here we see the exact same examples again that we saw earlier. So we have a path, then we're moving around doing Visual Odometry. If we have been to some place before, or like we have seen some pixels, some features in our images before, then we can actually say that now we're in a loop. Then we can close the loop, do global optimization, and we can get a way better result, like a more optimized path of our environment, or like map of our environment. So basically loop detection is reobserving a landmark after not seeing it for a long time. So if we have seen a landmark, we haven't seen it for long, we're reobserving it, then we can say like we have actually like a loop here, we have to get a loop, then we want to do some optimization to refine our path in that loop. It could also be that we're coming back to a previously seen or mapped area. It can be like we're storing features in like a bag of words, like visual bag of words. We've seen those features before. Then we say take the loop. Again, we do global optimization to get a better and more refined map of our environment from our camera poses. It can be found by looking at similarities between like the current frame and the past frame. So basically you just take a new frame in, you look at all the past frames that like try to compare the different kind of features. We can see here that the similarities can be computed by using like global or local image descriptors. So we can actually some descriptors trying to describe like, have we seen these before, how are these features matched to other features. Then we can look at past frames, keyframes, and so on to actually like do this loop detection, as we're going to talk about more in upcoming videos. So now we've been through all the theory here, and before we're going to jump into the code in Visual Studio Code, I'm just going to say here that all the code here that I'm going to show will be available here on my GitHub. You can just go into the GitHub link down in the description. You can just go into my GitHub, clone the repository, and then you can run the program or like the Python files and Python script here on your own computer, play around with it, try some other different kind of like image sequences. Maybe you can try your own image sequences and so on, but we need to use like calibrated cameras. If you want to know how we can calibrate your own cameras, everything here is on my GitHub as well, and on my YouTube channel. You can basically just go in and see the videos about camera calibration, do the camera calibration, use those parameters in these scripts here that I'm going to show, and then you can actually do visual odometry with your own camera in your own environment and see the results that you get. But in this video here, we're just going to use the sequences from the KITTI dataset. So when I jump into Visual Studio Code here, I'm going to go over the line of code in this visual odometry Python script that we have. So basically here, first of all, we need to import these different kind of modules that we need. So we need the operating system, NumPy, OpenCV. So we're going to do visual odometry with OpenCV. We're also going to import random, matplotlib, and so on. I also have some files in this lib folder here where we can do some visualizations later on to actually like plot, both play the trip, so play the sequence of images in our KITTI dataset, but also to do some plotting later on. I'll just provide you everything here. You can just go into my GitHub, download the repository here, and also the lib files here for the visualization. So in this video here, we're just going to go through the Python script here. We don't want to go into details about like how can we plot it, how can we play an image sequence here in OpenCV and so on. We're just going to see how can we implement visual odometry, and then we're just going to use these like folders and these files here, Python files, for doing plotting and playing the trip. We're also going to use TQDM here, so we're just going to import that. Then we're going to create a class with visual odometry. We have some initialization here up in our constructor. So basically here we just set our data directory. So this will be the path to our KITTI dataset sequence that we're going to use. So we're going to set that into our constructor here in our class when we're going to create an object later on to actually like run this program. So basically here we have our intrinsic parameters, we have our projection matrix from our camera. So here we just go in, load in our calibration files. So we're just going to create some methods here to load in these different kind of like information, calibration parameters, our ground truth poses that we can then compare with our estimated poses, and also the images that we have in our dataset or like in our KITTI dataset sequence. So here we just have a load calibration function, we have a load pose function and load images. Then we're just going to load in these text files, so we can just go in and see these text files here first of all. So we just start in the sequence one. We both have the left and the right image. So they actually like use their camera to capture these images, but we're just going to use the left images for our monocular case. Here we can basically just go in and see all the images that we have in this sequence. We have 50 images here in this sequence where we're just like driving straight on a road. We also have the KITTI Sequence 2 here where we're actually like driving around some corners as well. So here you have a calibration file. We have the parameters here of our camera. So these are just our intrinsic parameters and also the distortion parameters. And then we also have all the ground truth poses here for each of the individual 50 frames. So for each of the frames, we have a ground truth pose, and then we also want to estimate the pose. And then later on, we can actually like compare the ground truth to the estimated pose with our implementation of visual odometry. And then we can calculate the error and so on, which we're going to use this lib here. So we're going to use the visualization for plotting and also playing the trip. So this is basically everything we have. So we just have these functions to load in our intrinsic parameters, projection matrices, our ground truth poses, and our images. So here we basically have our ORB feature detector. So in this video, we're going to use ORB feature detector. We're just going to create that object here with OpenCV. So inside OpenCV, we have this ORB underscore create. We just specify 3000 here. You can play around with that parameter. Then down here, we have some other different kind of parameters for our feature descriptor. So when we have detected our features in our images, we also want to match those features. In this video here, we're going to use a flat-based matcher where we're just going to pass in these different kind of like index parameters and also our search parameters. So you can play around with these parameters here as well. These are just some default parameters that works really good on these sequences that I'm going to show you. So basically here, we just have a function for loading the calibration. We're just going to open up the file and then we're just going to read it in from the string or like read in from our text file here. Then we're going to specify our projection matrix and also our intrinsic parameters. And then we're just going to return that. And then we're going to have this load poses. We're going to load in the ground truth poses. Again, we just go into the file and then we load it in line by line. So we load in all the ground truth poses that I just showed you here in this text file. So we have that to compare to our estimated pose later on. Then we also have our load images function where we just go into the image path. We have our os.path.join. So we basically just go in, take all the images that we have in our folder, and then we're going to sort it. So we have it sequence by sequence. So we have like a sequence of images, like frame by frame. So we can just take the first frame, the second frame, the first frame, and then the next frame and so on. And then we can do tracking of different kind of features from those frames and calculate the pose of our camera. Then we're just going to inread those images with OpenCV here as we've done in all the other videos and so on as before. So basically just have inread, we specify the path, and then we return the images. So we are just going to read in all the images that we have in our image path. So in this example, we have 50 images in our image sequence. So this will return 50 images. Then we also have a function here to form a transformation. So we basically just, when we have our rotation and the translation estimated, we can just pass it into this function here, and then we will form a transformation matrix. So basically we're just going to transform our rotation and translation. We're going to combine it here, and then we're going to set it here down at the bottom, return the transformation that we can then use to do plotting and visualization. So basically these are all the different kind of functions here that we need in the start. So we're just going to use those functions. We haven't implemented anything yet. These are just like how to load in our data, and then we can play around with it later on. So down here, we're just going to take this one out here as well, and also the load images. And then the form transformation. So basically we need to get the matches here. So we have the ith element, which will actually just be our frame. So this function here, detect and compute key points and descriptors from the i-1th frame and also the ith frame using the class ORB feature detector. So we're going to use the ORB feature detector to do to compute our key points and descriptors in our images, and then we're going to use the flat-based matcher to actually like compare and match these descriptors that we get from our ORB feature detector. So down here we can see that I here is the index that we give to this function. So this is the current frame, and then we return Q1 and Q2 here, which is actually just a list or like an ND array, numpy array here with the good key points that we have matched position, matches position in i-1 frame, and also the key points here in the ith frame. So basically we have just one frame and another frame, and then we're going to return the key point from those because we want to triangulate those points later on, so we can actually do post estimation on those points. So to use this ORB detect and compute function, we just have our key points and the descriptors, which is equal to self.orb. So we go in and use the ORB feature detector. We're just going to use the implemented function here from OpenCV, detect and compute. Then we just pass in the image where we actually want to do this feature detection on. So this will be frame i-1. We're going to do the exact same thing here for our second frame. So basically now we have all the key points, the descriptors for both the first frame and the second frame in our sequence, and then we can actually match those descriptors together. So descriptors is actually just describing the key points that we found in our image. Then we want to match those because we want to track the features from one frame to the other frame, and then we're going to use our flat-based matcher down here. Inside the flat-based matcher, we're going to use KNN match, which is also implemented in OpenCV. So we can just directly use that. We pass in the descriptors, the first descriptor and the second descriptor, and then we can actually match those descriptors. We set a k value here, so we want to use k nearest neighbors. So we set k equal to 2 in this example, and then we just return all the matches here that we had. So down here, we can actually like sort or like filter out some of the bad matches that we have in our image, because if we have bad matches, it will just like we'll just get a larger error at the end. So basically here, we're just going to create a list with all the good matches that we have, and then we're going to set up something called the lows ratio test. So basically here, we're just going to go through all the matches that we found up here with our KNN matcher. We check if the distance here or for the M here. So basically here, we just take M and N, which is just like the features or like the key points here that we had when we're actually like matching it from one frame to the other. And then we're going to check if that distance is below some threshold value that we set. If they're close to each other, we say that this is actually like a point, they're really close to each other. And if they're further away from each other in the two image frames, then we say that this is not really a good match that we had. So we actually have false positive matches in our image. Then if we have good matches here, we just append our match to this good list, and then we can use this good list here later on to actually like get our key points and get the exact key points. So we get the good matches, or like we get the good key points from the first frame to the second frame, which is exactly what we do down here in these two lines. So basically we have our Q1 and the Q2, which is the good key point that we had in the first frame and in the second frame. So basically here we just go in and take the query index here. So we go in and take all the points in our key points, and then we're just going to take m.query index. So these are basically just indexes that we return. So we get all the good key points in the first image here, because we just have this for loop running m in good. So we run through all the good matches that we have in our key point, and then we're just taking all the points from those matches in our key points, and then we return our key points here into Q1 and Q2. So this is exactly the same thing that we do from the first frame to the second frame, but now we have Q1 here and Q2, which will contain all the good key points that we have tracked in the two frames, because these here are matched between the first frame and the second frame. So these key points here is actually like the same from the first image to the second image, with some false positives, of course, because we still have this threshold value up here that we can tune, but up here is actually just to filter out most of the outliers that we have in our image. We can set up some draw parameters here and also the draw matches, so we can then later on display what is going on. We can see all the matches from one image frame to the other image frame. So this will only be for visualization when we run the program later on. So this function here returns Q1 and Q2, which if you scroll up to the top is the good key points matches position in the I-1 frame and in the ith frame here. So down here we can go down, get the pose before. So we know that we need to find the essential matrix to actually like estimate the pose. To get this essential matrix, we just pass in the key points that we have from one image to the other image, and then we can actually like estimate or like find the essential matrix from those image points, when we also know the intrinsic parameters of our camera. So we need to make sure that we know the intrinsic parameters of our camera, or either you should actually like just calibrate your camera first of all, then you get directly the intrinsic parameters. We get Q1, Q2 here, and then basically we just pass it into the end as input parameters up here in the function. And then we get out a mask, and then we also get out the essential matrix, as we can see down here at the bottom. Then we can go down, use another function that we're just going to go through. So we're going to use decompose our essential matrix, because we know when we're decomposing our essential matrix, as I showed you in the slides in the start. So make sure, if you haven't seen the first part of the video here where we go through like the theory, make sure you check that out. We go through like why we're doing these things and so on, and what is the output when we're doing decomposition of our essential matrix. But basically here, when we do decompose, like when we decompose our essential matrix, we get out the rotation and the translation that we have estimated here from our essential matrix, or like from our poses. But we will actually get our 4 solutions here, as we talked about in the slides. So we need to use that later on. So we're just going to return our transformation, and then later on we're going to look at the transformation, see what is the transformation that results in most positive C values. So we actually like have all the points laying in front of our camera, because we know we get these 4 different kind of solutions. So here we just use an OpenCV function to find our essential matrix with our Q1, Q2, and our intrinsic parameters. Then we used our essential matrix down here together with our Q1 values and the Q2, which is again the key points in the first frame and in the second frame. And if we just go down to this function and see how we can decompose our essential matrix, we can see that we get in the essential matrix the good points, matches, and position in the 2 frames. And then we return here a list that contains the rotation matrix and also the translation vector, which is the output from when we decompose our essential matrix. So basically here we use an OpenCV function to decompose our essential matrix. we just pass in our essential matrix, we get out rotation 1, rotation 2, and then we also get the translation. So basically we only get one translation here because the other two solutions will just be the two rotations, and then we have the negative translation. So this is basically what we set up down here. So here we have the 4 transformations, and then we're going to apply a list here, or we're just going to put those on a list. So we're going to later on run through the list, check how many positive C values do we have. So here we're going to forward transformation of our rotation matrix and also our translation. So we have R1 with a positive translation, R2 with a positive translation, then we have R1 again with a negative translation, and R2 with the positive negative translation. So these are the four possible transformations that we get out when we decompose this essential matrix. And again, we want to find a solution where all the points is in front of our cameras, so we can use that transformation to generate our camera path or our robot trajectory in the environment. So here we're basically just transforming our K here, which is our intrinsic camera parameters. We just apply homogeneous, so we get homogeneous values instead. So we can then do linear algebra operations on our matrices and also our transformations later on. So down here we can get our projections. So we have a list of our projections. So we actually want to use all 4 different kind of solutions that we have. So we have these 4 transformations, and then we're just going to multiply that with our intrinsic parameters to do projections of our transformations with our camera. So that is why we need to have this homogeneous coordinates or homogeneous values for our K values, because we're going to multiply that with our transformation, where our transformation is also in homogeneous values. So then down here we can just set some print options here. So press equal to true. We go down here, create an empty list with positive values. So we want to see we want to get the most positive C values as possible. So down here, we're just going to have a for loop that we have P and T. We just run through our predictions and our transformations. So if we just go up here again, we have our transformations, which is our 4 solutions. And then we have our projections here, which is just our 4 transformation solutions multiplied with the intrinsic parameters of our camera. So then we can go down, triangulate our points, so we get our homogeneous Q1 values. And then we can just triangulate the points. We use our projection matrix from our camera, so our camera here, and then also the projection matrix here, or our projections that we got from our transformation. So we basically just run through all the P values here. This is some predefined projection that we got from our camera calibration. Then we have all these 4 different kind of P or projections that we're going to run through. And then we have Q1.T, Q2.T here. So basically we're just transposing our Q1 values and our Q2 values. And then we just want to triangulate those points out in the 3D world. So basically we just take image coordinates in one image and image coordinates in the second image, and then we just triangulate those to get some 3D world points. Then we get homogeneous Q1 values, and then to find homogeneous values in the second frame, we can just use our transformation, multiply that with our homogeneous values here in Q1 in the first image, because when we do that, it is actually just mapping or mapping the pixels or the points in the first frame, applying a transformation, because these transformations here is based on the feature detectors or the feature descriptors that we had from the one image to the other image, because we matched those early on. Then we're going to remove our homogeneous coordinates here. So basically we're just going to divide here the third column or the third index here in our values here, because that will just be the last value. We're going to divide all the values. So we're going to divide our X values, our Y values, and our C values by the homogeneous value here that we have in the bottom. So basically now we have just Q1s and Q2s here, which will just be 3D points. So we have the X, the Y, and the C coordinates in the 3D world when we're actually doing this operation here after we have triangulated our points. Then we can go down, look at the total sum. So basically again, we just want to get the total sum of all these points here that we have. So basically we just take the sum here and check if that is greater than 0, and then we're just going to sum it for the 2 points. So we both have the points, the 3D points in the first frame and in the second frame. We're just going to sum that up, and then we're going to compute the relative scale here, as I talked about in the slides as well, because we don't really have information when we only have a monocular camera. So we're going to calculate this relative scale. We're just going to take the mean value here of these norms here that where we're just using it from. This is just a standard formula for calculating relative scale here for 3D points in the first image, or seen from the first image and also from the second image. So these Q1s here is 3D points out in the real world. And then we're just going to calculate this relative scale that we can then use to like rectify or refine our total sum. So basically we just have our total sum plus our relative scale, and we're just going to append that to our positive vector up here. So basically we know we've found a solution when we find the transformation that yields the most positive C values here. So basically we have a vector here of all the values that we now have for each individual transformation. So we'll have 4 values, so we just need to go in, check which index has the most positive C values, and then we'll just take that index, and then we can just find the transformation up here, which is the result or like the ground truth or like the estimated pose of our camera. So this is the correct solution that we had. So down here at the bottom, we can actually see, we can just go in, take the argmax of our positive values. So we'll just go in on the list, check where is the maximum value, and then we're going to return the index on that. Then we can just go through all the indexes and return the right transformation that we have. So we want to find the transformation that gives the 3D points in front of the camera. So basically now we have estimated the pose of our camera when we return this rotation and also the translation. Then we can just form it into a translation, and we will get the exact estimation of our pose, like our camera pose. So basically now we have everything. We've been through the whole process here of setting up visual odometry, going from like, first of all, we have an image sequence. We do feature detection in the images. We track those features from one image to the other image. Then we do our, then we estimate and find our essential matrix. So how can we map points from one image to the other image? Then we can do decomposing our, then we can decompose our essential matrix to get the rotation, the translation. We get 4 possible solutions, and then we just have this code here to find the correct transformation from those 4 possible solutions, which will result in our camera pose or like our estimated camera pose that we can then use. And then when we do the exact same thing for the next frame, we can actually like calculate this iteratively or like incrementally, where we're estimating the pose of our camera and therefore the trajectory of our robot, car, or whatever we have attached our camera on. So now we can just go down to the main function here, set up these different kind of things, call the functions, set up the data directory and so on, and then we can just run the code, see how Visual Odometry works, and also like see how good our implementation works. So first of all here, we need to set the data directory. So this is basically the only input like argument that we need to give to our constructor here when we create our Visual Odometry object. So we just specify the KITTI Sequence it path here. So this is basically just this KITTI Sequence it here. We can also do KITTI Sequence 2 later on. But this is basically just the path here to the images, calibration file, and also the ground truth poses. So down here, we can just comment this in here because we want to play the trip. First of all, we're going to create a Visual Odometry object with our data directory. And then we're just going to play the trip here. So first of all, before we're going to do any operations, we're just going to play this sequence of images that we have in our KITTI Sequence 1 folder up here. So we can see what we're actually going to process. And then after that, we can go in, draw different kind of features that we're detecting, match it from one image to the other image. We can see actually like all the matches that we have. We're just going to delay it by some value so we can actually see what is going on. And then at the end, when everything is done, when we have been through all the frames, we can get up like these plotting tools and so on, as we talked about in the start. So we can actually like plot the ground truth poses and also the estimated pose that we have, calculate the error and so on. And then we can see like the results of our implementation here for Visual Odometry. So here we just have a vector or like a list here of the ground truth path and also the estimated path, and then we can compare that at the end. So here we're just going to have a for loop. We have I and we have the ground truth poses where we just run through the ground truth poses that we have inside of our Visual Odometry object. And then we just check here if I is equal to 0, we just have our current pose equal to the ground truth pose. So this will just be the first pose that we start with. Then for all the other poses here that we get in, we will actually like estimate the pose of our camera because we know the ground truth pose here, which is actually just the calibration, like our calibration parameters. Else here, if it's not 0, we will just run through I like up to 50 because we have 50 frames in this image sequence. So then we're going to get the matches here. We get into our Visual Odometry. We run this function get matches on I. So this will be the ith frame. So basically just have I here, which is corresponding to the frames that we have. Then we get our Q1 and the Q2 values, which is just the matches or like the good features that we match in the first frame to the other frame. And then we're going to get our pose. So we just call the get pose function. This is the function that does all like the triangulation, finding the correct solution of the 4 different kinds of solutions that are decomposing our essential matrix resulted after we have decomposed it. So we have a transformation here. We have our current pose is equal to when we multiply our current pose with the inverse of our transformation. That will be our current pose because we're looking one frame ahead when we're actually doing this transformation here. So to get the current pose, we just have the current pose multiplied with the inverse of our transformation. So this is how we find the current pose. Then here we just print out the current ground truth pose. We print the current pose, which is act like the estimated one that we can see up here. And then we can see the current pose used in the X, Y value here, where we can just go in, take those values like this. Then we're going to append the ground truth pose here to our ground truth path and also for our estimated path. So the ground truth pose and the current pose here will correspond with some X and Y values, so we can actually get the correct mapped environment out. So we're just going to draw it here on like a two-dimensional plot as we saw in the slides as well. So we're going to see it here. We're just going to plot the X and Y value for our ground truth path and also for the estimated path. And then we can calculate the error of those two and visualize it later on. So that's what we're going to do down here in our plotting. So we just go inside plotting, visualize path. So we just pass in our ground truth path and also the estimated path. And then we just have like a title here, Visual Odometry. And then here we just set an output file where we actually want to store it. We're just going to open up an HTML file. So we actually just open up HTML file and then we're just going to plot that on that window. So we're going to plot the ground truth path and the estimated path beside each other. So we can actually see how good is our estimated path compared to the ground truth path. And we will also calculate the error and display that as well on our HTML page here later on. So now we have everything. We've run through all the functions that we're using. Up here, we've been through the main function. We're getting the matches, we're getting the pose, we're calculating the current pose, and then we're actually just displaying it versus the ground truth path. So now we can go out, run the program here. We're going to use the image sequence one first of all. So here we run it. First of all, we will play the sequence here so we can actually see what is going on. So we go through all the frames here. We have 51 frames. So this is the image sequence that we're going to run. So now here we have run it through. Now we're going to do all the operations here on the images. We're printing out down here. We're printing out the transformation that we're actually estimating or the pose that we're estimating and also the position in the X, Y world coordinates here. So down here we can see where are we in the world from one frame to the other frame. Up here at the top we can see all these features here that we're detecting in one image. So we have one image here to the left and there's the second image here to the right. And then we're actually just matching these features here from one image to the other when we're going frame by frame in our image sequence and trying to estimate the pose. So every time here, right now, we just have a delay here of like, I think it's around like half a second. So every half a second, we just calculate and estimate a pose from these different kind of features here that we're detecting. So now when we're done running the program, we actually get up these plotting here in our HTML file. So over here to the left, we can see our path. We get our ground truth path, we get our prediction. So this is the estimated path that we have. And we also have an error here that's calculated between the ground truth and also the predictions. And over here to the right, we can just see the error that we're calculating. So when we're doing visual odometry with no slam, when we don't close the loop, we can't do global optimization in that way. So our error here for visual odometry, it will actually just be accumulating as we can see over here to the right. And as I said in the start of the video, but over here we can see we're actually like estimating a really nice trajectory here or like a really nice path here compared to the ground truth. We can see here, so these are actually like in meters. So we have a y direction here and we also have an x direction. So in this image sequence here, we actually just went straight. Which we can also see here that we estimated. So if you just zoom in a bit here in the start, we can see that we're actually like fluctuating a bit around here at ground truth, but we're still really close. So now we've zoomed in a lot. So it's actually like down to like, we can see here that this is 2 meters. So we have 1 meter here. So we're actually like down to centimeter precision on this image sequence here that we are running. So if we just go further here in the path, we can see we are still pretty close to the ground truth. We get some fluctuations, we get like some bigger errors over here, but then we come back to the ground truth here later on as well. And again, this is with no optimization. We're not doing any local optimization with bundle adjustment and so on, which we're going to cover in future videos. And then we can see here at the top, like at the end here, this is the last post that we're estimating, but we're not really at the end. The end is actually like up here. So we can see that this acts like a really, that's a fairly large error here at the end. So we think we're here, but the ground truth is actually like up here, which is why our error over here to the right is actually like kind of big, but we still follow the trajectory. We're just lagging a bit behind. We get some fluctuations and so on, but we can optimize it We can play around with it and so on, but this is just an example, and this is actually like a really nice estimate of our path here in the environment, but only using a monocular camera to do visual odometry. So the second example that I want to show is just the KITTI Sequence 2. So this is basically just where we're driving around in around some corners and so on. So this is a bit more complex data set than just going in a straight line. So again, we're just changing this from 1 to 2, and then we're just going to run the other file or like the other folder, and we're going to do the exact same operations. This is the only thing that we're changing, and then we're just going to see the results from the KITTI Sequence 2 dataset. We just hit play here. We're going to play the sequence here. So this is the sequence that we're going to match. So here we have 51 frames. Here we're matching all the different kind of like images, all the different kind of features that we're detecting in one image to the other image. So we can see we get all these unique features, we're matching in, and these are only the features that we after our threshold value. So we have this low ratio test that we set up. So we actually like have filled out some of our features here that we're matching from one image to the other. Again, we're printing out the same things. We're printing out the XY coordinate in the world when we're actually like estimating that, because we have all the 3D points, because we're reprojecting out, or like we're projecting out our points by doing the triangulation from one frame to the other, and then we're refining that with relative scale. So here we're just going to run through all the frames. We have 51 frames. Again, I've still added this delay so we can see what is going on here frame by frame. Here we can see the path. We start here at 0 and 0, and then we actually like move around in this shape here. And then we see we can actually get some really nice results here. We have a really low error here in the start, but then at the end we can see that our error here is accumulating, and this is basically just the same that happened as before. So here at the end we think that we are here, but we're actually like a bit further ahead, as we can see up here. But we still get some nice results. We're tracking, we're following the line like a ground truth here, really nice. In the start here, we're actually like really close to it. We fluctuate a bit back and forth between the ground truth. Here we get an error. We can actually like go in and investigate that if we want to, because this is actually like a really large jump up here. But then we can see like the more frames we get in, the closer again we come to the ground truth. Up here we are around the ground truth again, but then we think we're actually like here, but we should actually like be up here, because we have this slide here, or we have this big error down here at the bottom, so we don't really have information about these things up here. So this error here actually causes that we think that we're here instead of the end here. So we can go in and investigate what is going on here, try to optimize that, and then we can actually like get even closer to the ground truth. But if we just zoom in here a bit further here, or like a bit closer here to the start, we can see that this is actually like still a really nice estimate of our path here, or a trajectory in the environment. We can have larger image sequences. You can have like a whole data set. You can use the whole KITTI data set. We can play around with it. We can try to go around in loops, try to do loop detections and so on. So this is really nice implementation of Visual Odometry. Again, everything will be available on my GitHub. You can just go in there, take the code, you can just download it, to get like the repository, and the images and so on will be, all of the folders will be in there. So you can just go in, download it, run the files here. You can just change between sequence 1 and sequence 2 as we did, and then you can just run it and you will get the exact same results here. You can just play around with it, optimize it, and so on. So thank you guys for watching this video here, and remember to hit the subscribe button and bell notification under the video here, and also like this video here if you like the content and you want more in the future. It just really helps me and the YouTube channel out in a massive way. I'm currently also doing this computer vision tutorial where we're talking about like basic image operations, how we can actually like do all these things here that we have combined together in this project video here. So we're talking about like basic image operations, camera calibration, stereo vision, how we can get 3D information in our images with stereo vision, create point clouds, and so on. So if you want to know more details and more into theory behind all these different things we're talking about, we've also talked about feature detections, edge detection, corner detections, and so on. I'll link to the tutorial up here, or else I'll see you next video, guys. Bye for now.